Hello everybody, welcome to the next video on Physics at Home series. In this video we're going to take our discussion to Newton's second law of motion, and to do so we are going to utilize a pulley. This pulley here, I got it at Home Depot for $2.50, and this pulley is something that we can have access to, and we're going to use this pulley to in today's experiment. What we're going to do is take a string here and then drape over this pulley. So like this. Right. So drape over like this, and then two sides of this string we're gonna have these hooks. Okay. Now these hooks, both of them are pretty close to the same mass. So to create a difference between the masses, we will be using washers. Okay. Now, to mount this pulley, I'm going to show you in the next section that how to set up would be. But before we run the experiment, let me just make a comment here. This apparatus is called as an Atwood's machine, and in the Atwood's machine, it is assumed that the pulley doesn't play a part in the experiment. Okay, so theoretically the pulley would not. Okay, and they call that as an ideal pulley, which is frictionless, massless, doesn't have size, taken into the consideration and things like that. But in real life, the pulley that we are going to use, this one does have mass. Okay, so the pulley with this attachment here, if I put it on my weighing scale, so you cannot see, but if I do my fingers here, so you can see it's 35 grams. What you also want to show you is that there is friction on this shaft on which the pulley is sitting. So if I do this, so you can see that it came to stop. On the other hand, an academic pulley, something like this, which is sold by the academic store like Pasco Scientific, this pulley is, I think, $25 or $35. So it's a 10-time difference between the prices of the two. But look at this. It takes a long time for this one to stop. So this one also has friction, but this one, maybe we can see, it's much better than this pulley here. Okay, but we don't have $25, so we have to live with this pulley here. The other thing is, if I take the mass of this pulley with this attachment, then it's about 16 grams. So it's less than half of this one. Plus, you can see that this pulley itself, the 16 is pulley plus the attachment. So this one here is probably even less than 10 grams, so probably around 5 grams or so. So with this pulley, our, experiment would turn out much better. But since we are going to use this pulley here, we're going to have to, make some adjustments. Okay. So first thing would be, I would suggest that you take some cooking oil, and then maybe take some on your palm, and then put finger in it, and then dab here, and then here. Okay, and then let it turn. Okay, do it a couple of times so that the oil goes and sit on that shaft, and then reduces the friction in this pulley. Okay, and then in the next video I'm going to show you how to do the setup for this pulley. Okay. Now, as we are aware that not everybody would have a weighing scale at home, but in our first video we saw how we can use a spring to measure the mass. Okay, so the masses of these the masses of these hooks, the washers, all of these we can measure using the spring. Okay, so let's say in the next section, what does the setup look like? Okay, now here we can see how this pulley is mounted. So I put this pulley flat on this surface here, and I put tape on it, and then I put a book on this pulley so that now it stays at that spot. And I also put some cooking oil there, so you can see that So it spins a little bit longer than what it was earlier. Okay. Now the next thing would be to have our string, draped around it. Yeah. And then I have my two hooks. Right, so this is one, this is the other one. And you don't have to have hooks. Any two masses would work to run this experiment here. Okay, so as long as we know the masses, all of that should be all right. So if I could point this down, okay, so you can see now how these two are here. And what we need now also at this point of time is, as this, let's say the way it's going to work is we're going to create imbalance between the two masses. Okay, so for example, right now both of these rings have the same mass, so I'm going to put one washer here. Okay, and then if I let go, as you can see how this is gonna start moving, and we need this imbalance. And as it is doing so, we need to measure the time for rise of one or the fall of the other one. So let's go back here quickly, and let me put the rings here again. All right. And besides the time it takes for these to travel, what we also gonna need is the distance that these travel. Okay, so right now what we know is that this one here, let's say we're gonna put the washer on this one so that this will go down, and it's gonna travel whatever the distance there is. Yeah, so right now the other mass here is touching the floor. Okay, so it's touching the floor, and it's gonna rise until the other one will touch the floor. Yeah, so which turns out to be up to this height. Yeah, so what we want is a distance from here all the way to the bottom. Yeah, so we could use a string, okay, to get that distance. Okay, so just like we did in the projectile motion, when we created a plumb to measure the height of the table, we're going to do the same thing again. All right, so I have it here, and the distance covered. Okay, so up to this point. Okay, so I have the distance now, and I had measured it earlier. It is about 1.11 meter. Now, usually you have seen me sitting on my table, and that table has about this height, and which is about 0.7 meter, and this here is much longer as it travels, as we can realize. The reason being that the time it takes at some of these masses that we're going to use, the time it takes to rise or fall, whichever that we're looking at, is significantly fast. So to get a better handle on starting and stopping our stopwatch here, the longer the distance, the better we are at managing the start stop time. Okay, all right, so now that we have this, so the first there are two versions of this experiment that we're gonna do. Okay, so let's see in the next section what these two versions of the experiment are. In this slide here, we can see the Newton's second law written out right here. Net force on an object is equals to mass of the object times its acceleration. In this case, as you can see, there is a pulley, and then on the pulley there is a mass 1 and mass 2. So for this scenario, the net force will be the net force on this system together, okay, which is nothing but the difference between the masses times the gravitational acceleration. The mass is the total mass of the system, which is m1 plus m2. And acceleration is the acceleration of either object 1 or object 2. Okay. So if we look at this equation here, F equals to ma, then in the part 1, if mass stays the same, okay, if the mass does not change, then if the force increases, then acceleration increases, right, as we can see from this equation right here. Okay. So here is the table of 3 trials. Okay. Let's look at the total mass of the system. Okay. So the total mass, this will be 2 hooks plus 5 washers, right? This is for trial number 1. How much is the total mass for the second trial? There is still hook and hook, so there are 2 hooks, and then 1 washer on the mass 1 and 4 washers on mass 2, right? So it is still the same as trial 1, and in the final trial it is also 2 hooks and 5 washers. So we're maintaining the same mass of the system, but what we are changing is the net force. As we can see, the net force previously, the net force is the difference between the masses, right? So m2 minus m1, which is the mass of 1 washer multiplied by gravity, right? In the second case is the mass of 3 washers. That is the difference between the m1 and m2 multiplied by gravity, and then mass of 5 washers times gravity. Okay, so we are increasing the force, the net force on the system, and we are expecting the acceleration to increase as well. Okay. This is the part 1 of the experiment. The part 2 of the experiment, let's look at the mass total. So it's 2 hooks plus 1 washer. That's the first trial. Then we have 2 hooks plus 3 washers. And then 2 hooks plus 5 washers. So we can see here now the mass is increasing. Let's look at the net force on the system. Okay. So net force is again difference between the 2 masses. So you can see trial 1, the difference is mass of 1 washer multiplied by gravity, right? How about trial number 2? There is hook and 1 washer on the left and hook and 2 washers on the right. So we are back to the same net force, mass of 1 washer multiplied by gravity, and we repeat the same. So in part 2, okay, the net force stays the same. But what we are doing, we are increasing the total mass of the system. So if the mass is increasing, the acceleration should decrease. So we look at it here. F is constant, right? So if the value of the m would go up, then acceleration value should go down, because mass times acceleration is the force. Yeah, and if the force is constant, then we should expect that trend. In the first one, m is constant, so if f goes up, the acceleration goes up. Okay. So using these 2 experiments, we will be able to pin down that indeed the Newton's first law says that F equals to ma is the relationship between F, m, and a. Okay. So let's look at the video on how to run these trials. Okay, so we saw the two versions of the experiment that we're going to do. And in the first version, we're going to keep the total mass of the system constant. Okay, so the mass 1 and mass 2, both of these are going to be, total mass is going to be the same. All we're going to do is change the difference between the masses. Okay, so the way I'm going to do this is by using 5 washers. Okay, I'm going to put 3 on one side. Okay, and then I'm going to put 2 on the other side. Okay, so now I have, there is a difference between the masses now. And so what I would do now, lower the, the lighter mass here. Okay, and then run the experiment. Okay, so have my timer ready. And the count of 3, 1, 2, 3, go. Alright, so as you can see, sometimes this has a tendency to, come out of that pulley, and which is absolutely fine. We can always put that back on. But the thing that I'm concerned about is, for this mass is to hit this table, okay, as it goes down. So perhaps it might be a good idea, maybe I could switch the two. Again, this is a trial and error, so let's see. If I put the 3 masses here, or 3 washers here, and then 2 over there, and then rerun this experiment. Okay, so just make sure that the other mass stays, at that point. So the mass at the bottom, maybe I could turn the camera here so we all can see. Alright, so there you go. So the shadow, you can see that it is now, when the mass touches the floor, the shadow and the mass meet. Okay, and let's do this again. 1, 2, 3, start. Alright, so 187. Okay, oops, where did that go? Yeah, so 187 is the time. Let's repeat again. Let's see if we are able to duplicate the experiment. Okay, so get a close enough reading the second time as well. Reset. 1, 2, 3, go. Alright, 196. Oops, yeah, so 196. So it's pretty close. Okay, although I wish it could be closer, but I guess it is what it is. And then do the last one. So reset. 1, 2, 3. Oops. Yeah, 1, 2, 3, go. 196 again. Oops. So we got 3 of these readings now, and that would be called as trial number 1. Okay, so we know, the mass on one side, we know the mass on the other side as well, and the next thing that we're gonna now do is keep the total mass of the system same. Okay, but then take, a little bit mass from one side and add it to the other side. So essentially what we're doing is increasing the difference between the masses. So meaning increasing the total, the net force on this system. And if we run this, you probably would see that this is much, much faster now. Okay, and then the third trial, would be, take this one out, and then put one on the other, and that put on the other side. Okay, so we have, as you can see, 1, 2, 3, go. All right, so you can see it's pretty fast. Okay, so that will be the 3 trials. Okay, so this will be the part 1 of the experiment, where we keep the same mass but we increase the force. And what we would see is that if we increase the force, the acceleration of the system increases. Okay, so F and A, they are directly proportional to each other. If you maintain same mass, if F goes up, A goes up. The second part of this experiment is going to be keeping the same difference between the masses, but increasing the total mass of the system. Now the way we're going to do that is, on the first case, on the mass 1, just the ring here as is. On this, the second one here, we have the ring plus the washer. Okay, so right now the difference is the weight or mass of this washer. Okay, so we run 3 experiments, 3 runs, so that we get our time, as we can see. Right, so whatever the time it takes, then trial number 2 would be add 1 mass here and add a similar mass on the other side. Okay, so right now we have 2 on this side and then 1 on the other side. So difference is still the same of 1 washer, the mass of 1 washer. So now let's see what happens. So if, supposed to be down here. So if I let go, okay, whatever the time it takes, yeah. And then the third trial would be add another washer here and another washer here. Again, the difference between the masses is still the same, but the total mass of the system is increasing. Okay. Now let's see if we can see the if we spot any difference. Okay. So if we do this, you probably have realized that, or can see that as you increase the mass, the acceleration goes down. Okay, because what we are doing is, by keeping the same difference, we are keeping the net force on the system the constant. Okay, so this is how we're going to see the F, M, and A, how they are related to each other. Okay, so in the next section we're going to see analysis of these 3 trials. Now that we have run a trial for which these are the times, the 1.87, 0.96 and 1.96, average of the 3 is about 1.93 seconds. The 2 masses were 31.5 as M1 and 39 as M2. Now the first thing we're gonna calculate is acceleration using kinematics. So we know the distance this object here travels, right? So initial position is 0 and then it travels down, right? And the final position, the height in my case was 1.11 meters. And what we're going to use is the same equation that we have used before. The x2 equals to x1 v1 t half a t squared. Okay, since the blocks were released from rest, so we know the initial velocity is 0 meters per second. So this term zeroes out and this term zeroes out. Okay, so we're left with x2 equals to half a t squared. All right, so x2 is the distance covered is 1.11. Okay, equals to 1/2 times a times the time is 1.93 squared. Okay, so doing a little bit of algebra here, we get acceleration equals to 2 times 1.11 over 1.93 squared, and this turns out to be 0.596. Okay, so this is the acceleration right here using kinematics, 0.596. And what we're going to do is calculate the acceleration using second law. Okay. The second law gives us this equation, right? And if we reorganize, we have the acceleration as g m2 minus m1 divided by m1 plus m2. Now, word of caution here. Okay, this equation is derived using or assuming that the pulley is ideal. But in our case, the pulley is not ideal. Okay, so in which case, if we use this equation right here, then definitely we're going to get a number pretty far off than what we actually measured or measured using our experiment. So since the pulley is not ideal, so what we're going to do here, we are going to add another factor to account for the pulley's effect on this experiment. Okay, so which is about 0.7 times 35. So the pulley with its attachment is about 35 grams, and then about 70% of that is the actual pulley here. Okay, so this factor here is a close approximation of what the expression should be in a theoretical situation. Okay, so now let's use that equation. So 9.8 mass 2 is 39, mass 1 is 31.5 divided by 31.5 plus 39 plus 0.7 times 35. So this gives us expression as 0.77 meters per second squared. So as we can see, the two expressions here, they do not match. Okay, so definitely there is some percent error here. Okay. So that percent error now is the absolute value of the difference between the two accelerations divided by the expression that we expect this system to have multiplied by 100, and that turns out to be about 23%. Now this would seem to be high, pretty sure it's high. However, if we go on to the trial number 2 and trial number 3, then we would see that that percent error actually drops. Okay, and I tried these three trials, as we mentioned in the earlier video, when we have the two tables, and the error for the third trial came out to be about 1%. Okay, so see if the trend also you can also see the same trend, that the percent error goes down with trial 1, 2, and 3. Okay, that's for part 1. And same procedure or same calculations will be repeated for part 2 as well. And in the part 2, the percent error actually has a slightly different trend compared to what we might be able to see in part 1 of the experiment. Okay, but what is true is the fact that if we continue running these trials here, definitely one thing is for certain, is that in part 1, when the net force increases, the acceleration of the system will increase as well. And in part 2, if the mass increases, then the acceleration goes down. So whether or not, if we get a good percent error or not, but definitely we will be able to confirm that indeed the force on an object is equals to mass times its acceleration. Okay, So I hope you enjoyed this experiment, and next time will be an experiment on friction. Have a good one.